Section 9.5 Hybrid Orbitals. The VSEPR model, simple as it is, does a surprisingly good job at predicting molecular shape, despite the fact that there's no obvious relationship to filling shapes and atomic orbitals. For example, based on the shapes and orientations of the 2s and 2p orbitals on a carbon atom, it's not obvious why a methane molecule would have a tetrahedral geometry. How can we reconcile the notion that covalent bonds are formed from an overlap of atomic orbitals with the molecular geometries that come from the VSEPR model? To explain geometries, we assume that the atomic orbitals on an atom, usually the central atom, mix to form new orbitals called hybrid orbitals. The shape of any hybrid orbital is different from the shapes of the original atomic orbitals. The process of mixing atomic orbitals is called hybridization. The total number of atomic orbitals on an atom remains constant, however, and so the number of hybrid orbitals on an atom equals the number of atomic orbitals that are mixed. Let's examine the common types of hybridization, and as we do so, notice the connection between the type of hybridization and the 5 basic electrodomain geometries predicted by the VSEPR model: linear, triagonal planar, tetrahedral, triagonal bipyramidal, and octahedral. SP hybrid orbitals. To illustrate the process of hybridization, consider the beryllium fluoride molecule, which is generated when solid beryllium fluoride is heated to high temperatures. The Lewis structure of beryllium fluoride is: the VSEPR model correctly predicts the beryllium fluoride is linear with 2 identical beryllium fluoride bonds. How can we use the valence bond theory to describe the bonding? The electron configuration of fluorine, 1s2, 2s2, 2p5, indicates that there's an unpaired electron in the 2p orbital. This 2p electron can be paired with an unpaired electron from the beryllium atom to form a polar covalent bond. Which orbitals on the beryllium atom, however, overlap with those on the fluorine atoms to form the beryllium fluoride bonds? The orbital diagram for the ground state of beryllium atom is 1s2, 2s2. Because it has no unpaired electrons, the beryllium atom in its ground state is incapable of forming bonds with the fluoride ions. The beryllium atom could form 2 bonds, however, by promoting one of the 2s electrons to a 2p orbital. The beryllium atom now has 2 unpaired electrons and therefore can form 2 polar covalent bonds with the fluorine atoms. The 2 bonds would not be identical, however, because the beryllium 2s orbital would be used to form one of the bonds and the 2p orbital would be used to form the other. Therefore, although the promotion of an electron allows the beryllium fluoride bonds to form, we still do not have explained structure of beryllium fluoride. We can solve this dilemma by mixing the 2s orbitals with one of the 2p orbitals to generate 2 new orbitals, as shown in Figure 9.16. Figure 9.16, formation of sp hybrid orbitals. One s orbital and one p orbital can hybridize to form 2 equivalent sp hybrid orbitals. The 2 hybrid orbitals have their large lobes pointing in opposite directions 180 degrees apart. Like p orbitals, each of the new orbitals has 2 lobes. Unlike p orbitals, however, one lobe is much larger than the other. The 2 new orbitals are identical in shape, but their large lobes point in opposite directions. These 2 new orbitals are hybrid orbitals. Because we've hybridized one s and one p orbital, we call each hybrid an sp hybrid orbital. According to the valence bond model, a linear arrangement of electron domains implies sp hybridization. For a beryllium atom of beryllium fluoride, we write the orbital diagram for the formation of 2 sp hybrid orbitals as follows: 1s, 1sp, or 2sp. The electrons in the sp hybrid orbitals can form 2 electron bonds with 2 fluorine atoms. Because the sp hybrid orbitals are equivalent but point in opposite directions, BeF2 has 2 identical bonds and a linear geometry. The remaining two 2p orbitals remain unhybridized. sp2 and sp3 hybrid orbitals. Whenever we mix a certain number of atomic orbitals, we get the same number of hybrid orbitals. Each of these hybrid orbitals is equivalent to the others, but points in a different direction. Thus, mixing one 2s and one 2p orbital yields two equivalent sp hybrid orbitals that point in opposite directions. Other combinations of atomic orbitals can be hybridized to obtain different geometries. In boron trifluoride, for example, mixing two s's and the 2s and 2 of the 2p orbitals yields three equivalent sp2 hybrid orbitals. The three sp2 hybrid orbitals lie in the same plane, 120 degrees apart from one another. They are used to make three equivalent bonds with the three fluorine atoms, leading to the triagonal planar geometry of BF3. Notice that an unfilled 2p orbital remains unhybridized. This unhybridized orbital will be important when we discuss double bonds in section 9.6. Figure 9.18. Formation of sp2 hybrid orbitals. One s orbital and two p orbitals can hybridize to form three equivalent sp2 hybrid orbitals. The large lobes of the hybrid orbitals point towards the corners of an equilateral triangle. An s orbital can also mix with all three p orbitals in the same subshell. For example, the carbon atoms in methane forms four equivalent bonds with the four hydrogen atoms. We envision this process as resulting from the mixing of the 2s and all three 2p atomic orbitals of carbon to create four equivalent sp3 hybrid orbitals. Each sp3 hybrid orbital has a large lobe that points towards the vertex of a tetrahedron as shown in figure 9.19. Figure 9.19, formation of the sp3 hybrid orbitals. One s orbital and three p orbitals can hybridize to form four equivalent sp3 hybrid orbitals. The large lobes of the hybrid orbitals point towards the corners of a tetrahedron. These hybrid orbitals can be used to form two electron bonds by overlap with the atomic orbitals of the other atom, such as hydrogen. Using valence bond theory, we can describe the bonding of methane as the overlap of four equivalent sp3 hybrid orbitals on carbon with one s orbital and of the four hydrogen atoms to form four equivalent bonds. The idea of hybridization is used in a similar way to describe the bonding of molecules containing non-bonding pairs of electrons. In water, for example, the electron domain geometry around the central oxygen atom is approximately tetrahedral. Thus, the four electron pairs can be envisioned as occupying sp3 hybrid orbitals. Two of the hybrid orbitals contain the non-bonding pairs of electrons, while the other two are used to form bonds with hydrogen atoms, as shown in figure 9.20. Figure 9.20. The bonding in a water molecule can be envisioned as an sp3 hybridization on the orbitals of oxygen. Two of the four hybrid orbitals overlap with the 1s orbital of hydrogen to form covalent bonds. The other two hybrid orbitals are occupied by non-bonding pairs of electrons. Hybridization involving d orbitals. With the exception of helium, hydrogen, and helium, all atoms have 1s and 3p orbitals in their valence shell. Because the number of hybrid orbitals must equal the number of atomic orbitals to mix to form the hybrids, this fact would seem to limit the maximum number of hybrid orbitals to 4. How then can we apply the concept of hybridization to molecules where the central atom has more than an octet of electrons around it, such as phosphorus pentafluoride and sulfur hexafluoride? To do this, we turn to the unfilled d orbitals with the same value of the principal quantum number n. Mixing one s orbital, three p orbitals, and one d orbital leads to 5 sp3d hybrid orbitals. These hybrid orbitals are directed towards the vertices of a triagonal bipyramid. Similarly, mixing one s orbital, three p orbitals, and two d orbital gives 6 sp3d2 hybrid orbitals that are directed towards the vertices of an octahedron. The use of the d orbitals in constructing hybrid orbitals nicely corresponds to the notion of an expanded valence shell. Keep in mind, however, that only atoms in the third period and beyond, atoms beyond neon, possess vacant d orbitals that can be used to form hybrid orbitals of this type. The geometric arrangement characteristics of hybrid orbitals are summarized in Table 9.4. Hybrid orbit summary. Overall, hybrid orbitals provide a convenient model for using valence bond theory to describe covalent bonds in molecules with geometries that conform to the electron domain geometries predicted by the VS-EPR model. The picture of hybrid orbitals has limited predictive value. When we know the electron domain geometry, however, we can employ hybridization to describe the atomic orbitals used in the central atom of bonding. The following steps allow us to predict the hybrid orbitals used by an atom in bonding. Draw the Lewis structure for a molecule or ion. Determine the electron domain geometry using the VS-EPR model. Specify the hybrid orbitals needed to accommodate the electron pairs based on their geometric arrangement. These steps are illustrated in Figure 9.21, which shows the hybridization employed by nitrogen in ammonia is determined. Figure 9.21, bonding in ammonia. The hybrid orbitals used by nitrogen in the ammonia molecule are predicted by first drawing the Lewis structure, then using the VS-EPR model to determine the electron domain geometry, then specifying the hybrid orbitals that correspond to that geometry. This is essentially the same procedure that's used to determine molecular structure, except we shall focus on the orbitals used to make the bonds and to hold non-bonding pairs.